everyone is quite familiar with the arithmetic mean. Arithmetic mean is sum of the observations divided by number of observations. Okay, simply the sum of them, the n of them. This is the first, x1 is the first, x2 is the second, x3 is the third. It keeps on going, x4, x5 to a certain xn. All right, xn. So you divide by number of observations, the n of them. Geometric mean is the nth root of the product of the elements. All right, the nth root means the number of observations. That's what n is, the number of observations. All right. So x1 times x2 raised to, you take the nth root of it, or we say all raised to power 1 over n. And harmonic mean is simply the number of observations, which in this case is n, divided by the sum of the reciprocals of the given observations. Okay, so these are the facts we established in the last class, the information we obtained in the last class, and we're going to be using this moving forward. We're going to be saying some so this is the first thing we want to say in today's class. This is the quadratic mean, arithmetic mean, geometric mean, harmonic mean, inequality theorem. Okay, so what you see in red is the actual theorem. It simply says that for any given observation, it simply says for a given set of observation, the quadratic mean you compute.
So what does the max and min stand for?
What does it want?
So the max and minimum stand for.
I'm going to explain it. Okay. So I brought in max and minimum to, I'm going to explain what that means. But the theorem is actually what is in red, that for a given observation, we saw in the last class, when we're given a set of numbers and we computed the various means, we saw that the quadratic mean was greater than the arithmetic mean, or greater than geometric mean, was greater than the harmonic mean. Now, this is always true when you're given n observations and these observations are positive real numbers, all right? The quadratic mean of any given set of positive real numbers is always greater than or equal to the arithmetic mean, which is always greater than or equal to the geometric mean, which is always greater than or equal to the harmonic mean. So this is actually the QM, AM, GM inequality. So there are lots of other inequality we can pull out from here. Like we saw in the last class, we saw that the quadratic mean is greater or equal to the arithmetic mean. So in a problem, you could simply apply the fact that quadratic mean is greater or equal to arithmetic mean, okay, or arithmetic mean greater or equal to geometric mean, or geometric mean greater or equal to harmonic mean. Again, it's important to note that we can always say quadratic mean is greater or equal to any of the means, all right? So in a different problem, the idea you may choose to apply is quadratic mean is greater or equal to geometric mean, okay? That is, this theorem still says that quadratic mean is always greater or equal to every other mean to the right of it, okay? So we could, in a different problem, say quadratic mean is greater or equal to geometric mean, or we could say quadratic mean is greater or equal to harmonic mean, all right? Okay, we can equally say arithmetic mean, all right, is greater or equal to the harmonic mean. So this always observe the order. Quadratic mean is always greater than the rest of the mean stated. Same with arithmetic mean is always greater or equal to geometric mean or harmonic mean, and harmonic mean and geometric mean is greater or equal to harmonic mean. Now, this is maximum, this is minimum. I had mentioned this in the last class, and I said for a given observations, the maximum, okay, x1, x2, x3, whatever is the maximum among this set of values is always greater than any mean you compute, all right? The maximum observation among the n observation, the one that has the greatest value, okay, is always greater than or equal to any of the means you compute. And again, any of the means you compute is greater or equal to the minimum value among the observations you're given. Okay, so that's what the max and the mean means. Okay, so this like the main theorem is what is in red. I just brought max and means to re-echo what I said in the previous class. Now, in inequality, most problems on inequality has to do with proofs, all right? That's at the higher level. At the lower level, there's some inequality equations and we'll be asked to solve. But at higher levels of the Maths Olympiad, inequality problems always come in proof form, or you'll be asked to find the optimal point, the maximum or minimum value of a function. So these are some hints to what to look, what to do, what to try when you are attempting to prove an inequality problem. And I said if some of the variables occur, so if you see a certain sum like x1, x2, x3 plus xn, it's advisable you consider arithmetic mean. So you consider an inequality theorem involving arithmetic mean. So you could consider the QM-AM inequality, or the of course the AM-GM inequality, or the AM-HM inequality. Okay, these theorems involve the arithmetic mean. So whenever you see sum of terms, think along the line. Look at how you could bring arithmetic mean, the inequality theorem that has to do with arithmetic mean into the picture. Okay, now if some of the squares, if some of the squares of the variables occur, example a squared, b squared, okay, so you consider quadratic mean. So if you're having squares, the reason is simple. In a previous slide, we see quadratic mean has to do with sum of squares of given observation. So if you see it in a problem, you may consider looking for how you could bring quadratic mean into the picture. Okay, I'm going to do few examples to illustrate what I'm trying to say. All right, so if again you look and you're seeing in the problem, you're seeing if the product of variables occur, all right, example, you're having product of variables, you should consider bringing geometric mean, one of the inequality theorems that has to do with geometric mean, AM, GM, GM, so one of those inequality theorem that has to do with geometric mean, you consider bringing it into the picture. Now, if the sum of the inverses of the variables occurs, that's the inverse of variables. Okay, the variables you're given is A, B, C. The inverse 1 over A plus 1 over B. Of course, you should consider bringing harmonic mean into the picture. So based on what you're given, what you're asked to prove, you should consider bringing the relevant mean into the picture. Now, at foundational, at lower levels, these hints would always help you out. But at higher levels, they don't really help much. You have to look for more other algebraic manipulations to prove the inequality you're given. So we have this problem, given that A, B, C, D are positive real numbers, prove A plus B plus C plus D in brackets times 1 over A plus 1 over B plus 1 over C plus 1 over D is greater than or equal to 16, is greater or equal to 16. So we have to prove is greater or equal to 16. Now, so if you look at what we're asked to prove, you're seeing A plus B plus C plus D. Okay, so that gives you an idea of arithmetic mean. So we think of an inequality theorem that arithmetic mean is involved. Okay, so we note that arithmetic mean may be brought to play in this problem. Then in the second bracket, we are saying 1 over A plus 1 over B plus 1 over C plus 1 over D. Now, just like the hints we saw in the hint, so this our mind goes towards harmonic mean. Okay, and we know that arithmetic mean is greater or equal to harmonic mean. Okay, we have stated here arithmetic mean is greater or equal to harmonic mean from inequality theorem, and I've said we did a little proof of this theorem in the last class, not a complete proof, but we did a proof of just two given observation in the last class. So we have proved for a two observation case that arithmetic mean is greater or equal to harmonic mean. So now, because why are we bringing arithmetic mean and harmonic mean? Because of the nature of what we're asked to prove. Okay, so we start from what we know. So we know that for any given set of positive real numbers, the arithmetic mean is at least the geometric mean. That's the arithmetic mean is greater than or equal to the geometric mean. That would at least mean. So thus, now A, B, C, D. What's the arithmetic mean of A, B, C, D? There are 4 observations. There are 4 elements. So simply the sum of the 4 elements, A plus B plus C plus D, divided by 4. So that's the arithmetic mean, okay? Now, what's the geometric mean of A, B, C, D? All right, so again, there are 4 elements, so it's 4 divided by the sum of the reciprocals of the observations you're given. Okay, that's 1 over A plus 1 over B plus 1 over C plus 1 over D. Okay, so this we know from AM-HM inequality. So this is a fact. Arithmetic mean is greater or equal to what? The harmonic mean. Okay, but we're asked to prove. When you're asked to prove a thing, what you do is that you start from theorems on very well-known observation and do some manipulations to arrive at the final result. Okay, so what we've stated is true from AM HM inequality. AM HM inequality. This is harmonic mean, not geometric. So this is true from AM HM inequality. Now, one of the things you should note, I've not really been emphasizing the definitions of the variables we are given. These things are very important. Their definitions, sometimes you see positive real numbers, sometimes you see non-negative real numbers. In some very strange cases, you may see natural numbers. But another case that occurs quite often is you're told that these are sides of a polygon or sides of a triangle. Now, those constraints are very, very important. I'm going to bring it. So at this point, now I observe that this is this A plus B plus C plus D, and I need this on the left-hand side for me to have what I'm asked to prove. So I multiply both sides, I clear fractions, okay? I multiply both sides by the product of the denominators. Now we have 4 here, and we have 1 over A plus 1 over B plus 1 over C plus 1 over D. So I multiply both sides by the product of the denominator. That's 4 into 1 over A plus 1 over B plus 1 over C plus 1 over D. Now we need to ascertain, this is an inequality. And for those of you that have basic knowledge of inequality, we know that when you multiply both sides of an inequality by a negative value, the inequality sign changes. Okay, so we need to be certain that what we are multiplying both sides, it's a positive value. And we know that since A, B, C, D are positive real numbers, definitely their inverses are equally positive real numbers. The sum of their inverses would also be a positive real number. So 4 times, bracket open, 1 over A plus 1 over B plus 1 over C plus 1 over D is a positive real number. And so by multiplying both sides with it will not change the inequality sign. Okay, that's very, very important. So multiplying, we see 4, we'll take out 4. So we're left with A plus B plus C plus D times 1 over A plus 1 over B plus 1 over C plus 1 over D. On the right-hand side, we see that 1 over A plus 1 over B plus 1 over C plus 1 over D will cancel out itself. So we're left with 4 times 4, 16. And exactly that's what we're asked to prove. Prove, the Maths Olympiad exam at the highest level is more of a proof-based examination. The IMO took place a few days ago, and problem 2 was an inequality problem, and they were asked to do some sort of proving. So in proving, for those of us that have been introduced to it today, what it simply means is that you must start off with certain facts that are true and show that what you're asked to prove is true. In this case, we started off from the fact that arithmetic mean is greater or equal to harmonic mean. And what we did was just simplifying, and we got to the point where we achieved, our final result was what we are required to prove, and so we are done. All right, so it's always important you state your proof is completed when you're done, either QED or you just say, and that concludes the proof, and that's what we're asked to prove. It's very very important. So we move on. So this is a general case of the arithmetic mean, geometric mean inequality. So we said, okay, let's generalize it. The previous problem was just for four given observations. So let's consider when you're given n observations. We don't know n is of course a natural number. We see the arithmetic mean x1 plus x2 plus x3 plus LS plus xn divided by n. That's arithmetic mean. Arithmetic mean of a given set of observation is simply sum of the observations divided by number of those observations. So the arithmetic mean is greater or equal to the harmonic mean. So clearly, you see, if you multiply both sides by the product of the denominators, we are going to have this, okay, n squared. So we see that this is very important. So what we do is that subsequently, we don't need to go through this rigor. We could just, if we were conscious of the arithmetic mean, geometric mean inequality, we could have applied it directly. Because what the arithmetic mean, geometric mean inequality theorem is saying is that the product of the sum of the given observations and the sum of the reciprocals of the given observation is at least the square of the number of observations. That's what it's saying. And this is a very important theorem that we should take note of. The arithmetic mean, harmonic mean inequality. Whenever you see sum of given observations and in one bracket multiply to a second bracket which contains the sum of the inverses of the given observation, the result is always greater than or equal to n squared. So let's go back to this previous problem. So we see we're given A, B, C. This is the sum of A plus B plus C, the sum of the reciprocals from AM, HM inequality. There are 4. So the product will be at least 4 squared. And 4 squared is 16. Okay? So, but let me say this because in some countries, I've looked at, those of you here, I've kind of looked at the questions prevalent in your country. It's important to note that sometimes you'll be asked to prove some well-known inequality theorems, all right? And if you're asked to prove the theorem, you don't use the theorem to prove itself. If you're asked to prove the AM-HM inequality, you don't use the theorem to prove itself. So what you simply do is that you use more obvious theorems to prove less obvious theorems, all right? Okay, this is foundational class. So I have actually the proof of a AM-HM inequality. I can argue that it's in the previous notes. Yeah, because for two given observations, all right. If you're asked to prove for more than 2 given observations, then it's of an intermediate or an advanced level of Olympiad exam, which this class is not designed for. Okay, so let's move on and see how we do some proofs in other contexts. So we have, given that A, B, C are non-negative real numbers, okay, this time around, the previous example, we saw that the unknowns were positive real numbers. Here we are saying non-negative real numbers. That means A, B, C can be 0 or any positive real number. So we're asked to prove that A squared plus B squared plus C squared is greater or equal to AB plus BC plus C. Now, let me say that these are very basic Olympia. These are well known. For those of you that are not new to Math Olympia, particularly inequality, you must have come across this problem before. There are more than 4 or 5 ways to prove this inequality. There are so many ways to prove this inequality, so many. However, I'm going to just do one, just show one proof method, and that's because I want to emphasize what I've already said so far. I want to re-emphasize it, okay? So what I simply do is that I look at, we said, I gave you hints at the beginning of the class, so I want to use those hints in proving this problem. Now, we said when you see sum of squares of the variables you're given, of the observations you're given, you should consider QM, okay? Now, there are hints, there are no rules, okay? Now, but if you consider QM in this case, it won't work, all right? QM, okay, my proof doesn't make use of QM. Someone could, of course, go through the rigors of using QM and it will work, but it's going to be unnecessary because the journey will be unnecessarily long. The solutions, the proof will be unnecessarily long. So QM doesn't really work in this case. So we now go over to the right-hand side. Perhaps we may get some motivations from the right-hand side. Now, on the right-hand side, we are seeing a product, AB. Whenever you see product, our minds goes to geometric mean, all right? Now, if we consider AB, now geometric mean doesn't, is always root of the thing. So since we're having product of 2 things, it means that for this to be in a geometric mean format, square root must be involved, all right? So AB, how do we bring it? Okay, let's just look at the right-hand side of where my pointer is. So AB is the same thing as square root of A squared B squared, all right? So this is some motivation. So on the right-hand side, we are saying A squared B square root of A squared times B squared. So if we are going to consider geometric mean of AB, all right, we are looking at AB as A squared times B squared. So that simply means that AB is the geometric mean of A squared and B squared. So the variables that result in AB is simply A squared and B squared taking the geometric mean. So since we're talking about geometric mean on the right-hand side, we now think of, okay, so let us consider a scenario where we consider the arithmetic mean of A squared and B squared. Now, let me say this, the first thing you may think about, the first thought that may come to you that you choose to try out may not necessarily work. So oftentimes you need to try many stuff before something finally works. Okay, so clearly we've seen that we work with a squared b squared. All right, so we now say from AMGM inequality we know that a squared b squared is the focus. Now the arithmetic mean of a squared and b squared is greater or equal to the geometric mean of a squared and b squared. The arithmetic mean of a squared and b squared is simply a squared plus b squared divided by 2. The geometric mean of a squared and b squared is the square root of a squared times b squared. Okay, let's not forget arithmetic mean is simply sum of the observation divided by the number of observations. Geometric mean is what? The of 2 observations is simply the square root of the product of the observations. All right, so the observations here are not a and b but rather a squared and b squared, so there are just 2 of them, so you sum them divided by 2. For geometric mean, the square root of a squared times b squared. Okay, so we have a squared plus b squared divided by 2 is greater than or equal to the square root of a squared times b squared, which simplifies and gives us ab. So similarly, we see, okay, a squared b squared works. All right, so we choose to try, okay, we can also involve a squared, c squared, b squared, c squared. Now, oftentimes you may not be certain that what you're doing will result to the final result. Most importantly, if you're very, this is very new to you. So, but you just try stuffs and see if it works, if it gives you the final desired outcome. So since we have a squared plus b squared, okay, we say similarly, the same thing holds for b squared plus c squared. The arithmetic mean of b squared and c squared is greater than or equal to the geometric mean of b squared and c squared. The arithmetic mean of b squared and c squared is simply b squared plus b squared divided by 2. The geometric mean of b squared and c squared is the square root of b squared times c squared, which is bc. Okay? The same thing, c squared plus a squared divided by 2 is greater or equal to the square root of c squared times a squared, which is ca. So these results are true from the AMGM inequality theorem. All right? So because when you're proving an inequality, you need to make use of relevant theorems. Now, having gotten these 3 inequalities, okay, we are adding the above 3 inequalities we have. So when you add the above 3 inequalities, this is exactly what I have. AB plus BC plus CA is the right-hand side, and the left-hand side is this. So quickly, you see that the denominators are the same. So you can go ahead and add the numerator. So you have a squared. So you're going to have 2a squared, 2b squared, 2c squared, and that will simplify to become a squared plus b squared plus c squared greater or equal to ab plus bc plus c, and that concludes our proof. Okay, so you feel free to ask your questions. If you have any question, you could raise your hand or turn on your mic, and I will hear you out. If there's an issue, something I've mentioned, you're not really, you don't really understand. But what I want you to note is that in terms of proving inequalities, all you need to use is that you need to look for a theorem that works at the foundation, at the beginning level. Yeah, that's the trick. Okay, you have to look for a theorem that fits in. And how do you find the theorem that fits in? By observing what you're asked to prove. Okay, so we observe the left hand side. We're thinking along quadratic mean, and I said it won't work. So we went to the right hand side. Okay, there are 2 things to see on the right hand side: the sum of the terms and the product of each term. So we chose to look at the product a times b, and we said a times b, that's geometric mean. So, but if it's 2 terms, we expect square root of the product of 2 things, and we said, okay, let's transform a times b to a form where it's square root of the product of 2 things, and that was simply square root of a squared times b squared. We said, okay, and since we saw a squared and b squared on the left hand side, okay, we said, okay, definitely let's now work with a squared and b squared. What's the arithmetic mean of a squared and b squared? A squared plus b squared divided by 2. What's the geometric mean of a squared and b squared? Square root of a squared, and we say, okay, that is the idea that works. The arithmetic geometric mean inequality theorem is the idea that works in this problem. So we now did some fine-tuning here and there. We simplified, and we are done. All right. So let's now solve the last problem for today. This is to find the minimum value of f of x. This actually, I restructured this question. This is the famous Nisbet inequality. For those of you that are you've been involved in the Math Olympia for a while, you must have come across this inequality. In fact, there is a follow-up problem. If A, B, and C, if you take them to be sides of a triangle, all right, it has a maximum value. All right, if you take A, B, and C to be sides of a triangle, it has a maximum value. But that's not what we're solving now. What we're solving now is we want to find the minimum value of f of x. all right? Minimum value of f of x. F of x also have a maximum value if we restrict a, b, and c not just as positive real numbers, but also as sides of a triangle. All right. So we're bringing the constraint that a, b, and c, besides being positive real numbers, they're also sides of some triangle. It f of x has a maximum value. Okay, but let's focus on what we have here. So we want to find. So whenever you have to find minimum or maximum value, inequality can be of help. Of course, for those of us that are in higher classes, we know that when we hear maximum, minimum, our mind runs to differentiation, calculus. All right. Again, it's possible to bring in such arguments in when you have to prove inequality, or you have to find rather minimum value, maximum value. Now, what exactly do we do? What exactly do we do? We want to find the minimum value of f of x. So f of x is a over b plus c b over c plus a plus c over a plus b. Now there's symmetry. Symmetry is an attribute that you should take very seriously when you are solving more difficult Olympiad inequality problem. But for this class, you need not worry yourself. So the issue is that what do we do? What do we try? What do we attempt? Okay. For problems such as this, if for you being a newcomer to the Olympiad, it will take you quite a while to figure out what to do. Again, there are many ways to solve this. There are like 8 different solutions to this, but I'm just going to do one. So the approach I choose to follow is, okay, we could we observe that in each term, a over b plus c, we clearly see that the variables at the denominator and numerator are distinct. Okay, are distinct. And we know that it's easy to play around with the numerator than with the denominator. So the first attempt is that we make each fraction, that's each of these, have the same numerator. Okay, and so we see that, okay, if for the numerator, for the first fraction we have here, a over b plus c. Now we see if we bring b plus c at the numerator level, we have a plus b plus c. In the second fraction, we bring c plus a, we have a plus b plus c. In the third fraction, you bring a plus b, we have a plus b plus c. So you see, it is possible. Now, in the first fraction, b plus c is simply the denominator. The same thing, c plus a for the second fraction simply did. So we see that, okay, and b plus c over b plus c is 1. So what do we do? Let's add 1 to each fraction. So we have plus 1, plus 1, plus 1. Now, the reason we're adding 1 is because of what I've just said we should do. We want to attempt to make each fraction have the same numerator. So hopefully, if we get that, we can build on it. Okay. So we added 1 to each fraction, but by adding 1 to each fraction, you have changed the question. All right. So this is 1, 2, 3. So we subtract 3. So by subtracting 3, it's like we haven't changed anything. So 1 plus 1 plus 1 is 3. 3 minus 3 is 0. But what we now do is that we keep the negative 3 aside and build on what the plus 1 would do. So plus 1, for the first fraction, we say our plus 1 is the same thing as b plus c over b plus c. Of course, you know our b plus c cancels b plus c, and we have 1. All right. For the second fraction, the plus 1 to it is c plus a over c plus a. For the third fraction, it's a plus b over a plus b. Okay. So we see that the first 2 fractions simplifies and becomes a plus b plus c divided by b plus c. Okay, the denominators are the same, so you can directly add the numerators. All right, so we have that. Now for the third and fourth fraction, we see that the denominators are the same, c plus a, so we can directly add the numerators, and if you add them and rearrange them, you also have a plus b plus c divided by c plus a. Now for the last 2 fractions, the same thing plays out. The denominators are the same, a plus b, so we can directly add the numerators, and if you do that, you have a plus b plus c, all right, divided by a plus b. Of course, do not forget your minus 3. So we see the numerator in the first, in the second, and third, they're all the same. So we factor it out. Okay. So when you factor it out, you have a plus b plus c times, this is 1 over b plus c plus 1 over c plus a plus 1 over a plus b. Okay. Now what do we do from here? Of course, your minus 3. What do we do from here? Now we think of what to do. Now we carefully observe a plus b plus c. That is sum. So arithmetic mean comes to our mind, but it has to tally with the second bracket. We see 1 over b plus c, 1 over c. So we're not seeing 1 over a plus 1 over b plus 1 over c. If we saw it, we'll have said, yeah, we are there, am, hm inequality. But we are seeing something else. What are we seeing? 1 over b plus c plus 1 over C plus A plus 1 over A plus B. Now, after some times or after much think, we said, okay, but we can still work with AM-HM inequality. Let's see how we can, since the inverses, what we have in the second bracket is sum of inverses of B plus C, C plus A plus B. Okay, so let's work towards having it in the first bracket. Let's see how we can work on the first bracket for it to become sum of B plus C, C plus A, and A plus B. Then we can now apply the AM-HM inequality. Okay, so we looked at A plus B plus A plus B plus C. We want it to become B plus C plus C plus A plus A plus B. So first of all, we just add up. Okay, let's say we add up all what we want it to become. Now, when we add it up, we see we simply have, this will be, it's going to be 2A, 2B, 2C. All right. So we know that if this is 2A, 2B, 2C, we can rearrange it to be what we want. What do we want? We want B plus C plus A plus A plus B. So we want, so the first thing we did is that we transformed this to be 2A plus 2B plus 2C, but at the same time not changing the question, not changing what we have. So we see that 2A plus 2B plus 2C divided by 2 is the same thing as A plus B plus C. Okay, same thing as A plus B. So we're at this point. Now, don't forget that 2A, 2B, 2C is what we wanted. So what do? With 1 over 2, we bring out our half. So we bring out half, we have half out, we factor it out, half, and we now 2A plus 2B plus 2C, we express it in the form such that we can clearly see our AM-HM inequality, which was what we saw, what we imagined at this point. So we see that 2A plus 2B plus 2C is the same thing as B plus C plus C plus A plus A plus B. If you simplify this, you're going to have 2A plus 2B plus 2C. Now, this form clearly, we are seeing a scenario of AM-HM inequality. Do not forget what AM-HM inequality says. It says that the sum of a given observation, the product of a sum of a given observation multiplied by the sum of the inverses is at least the number of observations squared. Now, you know, your mind, have a free mind. It's not always it is A plus B plus C, okay? Sometimes it could be A squared plus AQ plus A raised to the power 4. Those could be the sum of the observations you're given. So always having a free mind. So in this case, the observations are B plus C, C plus A plus B. So clearly we see that we have the sum of the observations in the first bracket. The second bracket is the sum of the inverses of the observation. In this case, B plus C, C plus A plus B. So from AM-HM inequality, we know that the product of the two brackets, okay, that's the first, this bracket and next bracket, is at least 3 squared, since there are 3 observations. Of course, the observations are specified. They are put in braces. Now, so far, we were simplifying, all right? So we use the equality sign all along because we were simplifying. So at this point, we're now bringing in an inequality theorem, all right? And we know that the arithmetic mean AM-HM inequality, we established that in the beginning of the class, that AM-HM inequality simply states that the sum of given observations, the product of the sum of given observations, and the sum of the inverses is at least the number of observations.
Hello, sir.
Is at least okay. Sorry about that. So we see that the sum is at least number of observations squared. So in this case, it's 3 squared. So you please observe closely that I'm going to replace the 2 brackets with 3 squared. And of course, what I'm saying is that this expression is at least when it is replaced with 3 squared based on the AM-HM inequality. So we have half 3 squared minus 3. Okay. Now if you simplify this, 3 squared is 9. Half of 9 minus 3. If you simplify it, you have 3 over 2. Okay. So clearly, f of x was the starting point. Okay. So we see that f of x is at greater than or equal to what? 3/2. So therefore, the minimum value of f of x is 3/2. Yeah, I had someone asking a question. I think we have very few seconds left. Can I hear you out? Let's see if I can answer your question before we go off. Hello, someone asking a question. Who was the person? Okay, so I hope that our class is over. I hope you've learned a thing or two. So we'll meet again next time, same time next week.
So what are we going to do next week?
I would let you know on or before